Except that. Your button there. Oh, yeah.
Oh.
And you have to do the high flooding meeting before. I don't assume this again.
That look familiar? Does.
Well, as people are trickling, let's get started. So I'm delighted to welcome my friend and classmate, Professor Meredith Hughes, to upon a campaign. Meredith has done all of this. She asked me to make sure I remembered bio details. Checking. So let me see if I get this right. Graduated summa cum laude from Yale. Went on to Harvard, small private university and graduated in 5 years. Won the Feynman Prize for the best thesis. Won the Bach Prize for best thesis for anybody under 35 years. Went to Berkeley, which is another small public university that had a Miller Fellowship for 2 years. And then straight away went to a faculty position at Wesleyan, where he is currently an associate professor and also department chair. And since I know, kind of remember all the fun details about Meredith, I could also let you know, she, in addition to doing all of the cool science that I'll tell you about today on disk systems, was also the star volunteer at the Museum of Science in Boston, and had, among other things, an owl named Sigmund that would peck at all of the guys that he brought over, including me, but did absolutely anything Meredith commanded. So, master of all things, avian and all things. Please take it away.
Thank you so much. I've never had a better introduction than that, I think. So thank you all for having me here. It's been a delightful visit. I've really enjoyed getting to know your department while I'm here. I always like to start off my presentation with 2 images, one that represents the science that I do and one that represents the technique. I should say, speaking of images, that throughout this talk, I like to show pictures of the students I've worked with who've done the research. And I thought about going in and updating David and Kale's pictures to something a little more recent, but then I thought, nah, I'm going to show them. So you guys get to see them as I knew them when they were undergrads. So you can anticipate those wonderful moments. Okay, so the science that I do, this is actually the research that Kale, well, it's the same disk that Kale and David both worked on, but this is an edge-on debris disk around a nearby young star. It's called AU microscopy. I'll talk a lot more about it later on. And the technique that I use is millimeter wavelength interferometry, which my name pulls to Newcastle here, and you guys know all about millimeter wavelength interferometry, but this is Alma. I'll also mention it. I'll say a few more words about it a little bit later on, just to jog your memory a little bit. Okay, but I wanted to start off with this question of what are debris disks and why should you care? So debris disks are beautiful. We have them in our own solar system. So this is one particular view of a debris disk from Spain, Sierra Nevada National Park in Spain. And the zodiacal light is right here. How many of you have ever seen the zodiacal light with your eyes? I'm curious. 3. Okay, you all have a homework assignment. I hear there's a dark sky site near this campus. So you have to go out and on a dark night, look towards the west right after sunset. You might see the Milky Way, but you might also see another band of light stretching up from the horizon, and that's the zodiacal light. So our solar system has not 1, but 2 debris disks. The zodiacal light looks the brightest to us because we're sitting inside it, basically. This is dust that's generated by collisions between Jupiter family comets and asteroids in the inner solar system. But actually, if we were alien astronomers looking back at our star from a distant star, the brighter debris disk would actually be the Kuiper belt. So the Kuiper belt, objects in the Kuiper belt produce dust. And because the dust, those are large objects, they collide, and the dust covers a large area, that would actually be the brighter debris disk from a distant star. Although actually, if we were the alien astronomers looking back at our own star, what we would really see is nothing, because our current technology is not sensitive enough to detect our own debris disk around another star. So all of the debris disks that I'll show you in this talk are basically scaled up analogs of the Kuiper belt that are more massive than the debris disk in our own planetary system. Okay. So what is and is not a debris disk? I'm going to ask you guys. Are you ready? Okay, this is your quiz before I've told you anything, just to kind of see what people think about debris disks. Don't be embarrassed if you don't know the answers to these questions, but I want to kind of get a sense of how much you know about debris disks or what kind of ideas are sort of floating around up there. Okay, so I'm going to ask you to raise hands. To what extent are debris disks gas-free as far as we can detect? How many people think that they are never gas-free, that there's always gas in debris disks? How about sometimes? All right, you're hedging your bets a little bit. Okay, I like that. How about always? Okay, we've only got one. Okay, so or two. When I gave this, when I would do this a few years ago, people who know about debris disks would say always gas-free, because it used to be the case that debris disks were defined by their lack of gas. But one of the things that Alma has taught us over the last 10 years is that actually a number of debris disks still have detectable amounts of gas, and that's going to be something that I'll talk about later in the presentation. So the correct answer here is sometimes. To what extent are debris disks older than protoplanetary disks? How many people think never? Stephen. How many people think sometimes? How many people think always? That seems like the right answer, right? But actually, we now know that there are debris disks in even some of the youngest planet-forming regions. So for example, people have found debris disks in Taurus and Lupus, which are younger. They're only about 2 to 3 million years old. And we think of those as nearby star-forming regions that have protoplanetary disks. But actually, it turns out that some systems go through this evolution to the debris disk phase quickly. So the correct answer is sometimes. So these used to be the two criteria by which we defined debris disks, that they were gas-free and they were old. So, and we can't do that anymore. We know too much now. It's too complicated. Oh no. Okay, so I have another question for you. To what extent do debris disks have optically thin dust at all wavelengths? How many people think never? How many people think sometimes? How many people think always? The correct answer is always. Joaquin, good. I told you the answer to this when we were talking. So debris disks always have optically thin dust at all wavelengths. We think, in fact, that this is a hallmark of a debris disk. Protoplanetary disks tend to be optically thick at optical wavelengths and near-infrared wavelengths, and optically thin only at longer wavelengths. Although we're not even sure they're optically thin at millimeter wavelengths because they got all these rings and stuff. We'll talk about that later.
Based off one annual review.
I know, right? Yeah. How much can you trust one annual review article written by people at Wesleyan? To what extent are debris disks undergoing destructive collisions? How many people think never? Sometimes. Always. Okay, so we think this is always true. So this is the other hallmark of debris disks, that when you look at the lifetime of a dust grain in orbit around a star in a debris disk, it's like, if you calculate the lifetime, it's actually shorter than the age of the star. So that means that it can't have been there since the birth of the star. It has to have been generated by some kind of destructive process. So we basically think that all debris disks are, the hallmarks that define debris disks are that they are optically thin at all wavelengths, and they're dominated by destructive processes rather than protoplanetary disks, which might have some destruction going on. But overall, you're building up planets and you're rearranging planetary systems during the protoplanetary disk phase. Whereas during the debris disk phase, the planetary system has already formed, and the dust that we see is generated through destructions of existing planetesimal. Yeah.
For the first two, is it usually?
Usually, yes.
Yeah.
I would say, yeah. Well, I don't know, actually, the gas thing. I was joking for a while in the early days of Alma that observe an A-star debris disk with Alma, get gas for free. Because actually the detection rate for gas around A-star debris disks is really high. It's at least 50%, I think, or at least it was in the early days. And it's lower for the less luminous systems, but that might also be because it's harder to observe in the less luminous. So, okay, so just to kind of put this into a larger picture of star and planet formation for you, we all know that stars form in giant molecular clouds of gas and dust. The dense parts of those clouds collapse under the influence of gravity. You get this extremely confusing stage where you have a protostar, maybe there's a pseudo disk, maybe there's an envelope that's falling onto the disk, maybe there are outflows. I'm glad I don't study this stage. And then it all settles down into what we would call a protoplanetary disk, a Kinematic sequence star surrounded by a Keplerian disk of gas and dust. And eventually that disk dissipates and you wind up with something that looks like our solar system, a main sequence star, probably including a debris disk, possibly including planets. And another kind of fun fact about debris disks that I'll mention is that if you go out and you do a volume limited survey of stars near the sun and you ask how many of those stars, what fraction have detectable debris disks, remember that we can't detect our own debris disks, so this is just the tip of the iceberg. The answer is about 25 to 30% of nearby stars have debris disks. So since we know we're only detecting the most massive ones, we basically think every star has a debris disk. So probably they all look more or less like our solar system, with planets, a debris disk, and a main sequence star in the middle. So I'm going to be focusing on this stage today in case you haven't gotten that impression already. And here's another view of the zodiacal light, just because I think that's pretty cool. Okay, so that's what a debris disk is. The other part of that question is, why should you care? Well, if you care about planets, and you should because you live on one, then you should think about how they form and where they came from, right? We want to know where they came from. So this is a concept that I got from Phil Armitage, and he came and he showed this plot as a way of thinking about, all right, in terms of age, protoplanetary disks cover kind of the first 10 million years of evolution. Most, but not all, of the planetary systems that we know of are older than 1 billion years, right, around mature stars. And if you think about grain size, protoplanetary disks take you kind of up to the centimeter regime, and then there's nothing until you get up to 100 kilometers. And Phil used this as like, look, there's this giant gap in the middle here, and we don't know anything, and it's such a big mystery. And I said, Phil, debris disks are in that gap, right? So debris disks actually bridge the gap between what's happening at these young ages in protoplanetary disks and what's happening in these older ages. And actually, if I could have stretched this out further, it really extends all the way to infinity, because we've seen debris disks around stars that are several billion years old. So it doesn't end at 1 billion years, but most of the debris disks that we see are tens to hundreds of millions of years old. So it's this important gap, and really the holy grail of planet formation research is understanding how we go from the initial conditions and the early system conditions that are in protoplanetary disks to the mature planetary systems that we're seeing with exoplanet surveys. And the debris disks are a really important intermediate piece of that puzzle because they span that intermediate gap. Okay.
Oh, I lost the sound. But I was going to ask you. You said that it goes to infinity. Are there white dwarfs that have debris disks? So it goes all the way out to when you have a white dwarf.
There are white dwarfs with debris disks. That's a great point. Yes. So it goes all the way to the end of the star's life and beyond. And we don't know actually, is that leftovers of the same planetary system? Is there kind of a second generation planet formation process that occurs at these later stages? We don't know the answer to that. But yeah, you're absolutely right. There are debris disks around white dwarfs.
And I meant to ask you that because you said one feature of the debris disks that we're studying now is that there's always destructive collisions. Yeah. But around white dwarfs, I'd expect the radiation pressure to be destroying the dust very, very quickly.
Yeah, well, okay. So that's a good question. Although I think so the dust has to come from somewhere right before the star can destroy it. And I think that dust has to come from some sort of destructive process, because as you're pointing out, the lifetimes are going to be short, although it's for different reasons at those late stages than at the earlier stages. So you still need some kind of destructive process to produce the dust before you can destroy it. Yeah. Okay. So we've got optically thick growing dust and protoplanetary disks like HH30. You can see it's really puffy. Then around debris disks, these are main sequence stars, less gas. Actually, some of the younger ones may actually have comparable amounts of gas to protoplanetary disks, which is interesting. But the dust is optically thin, and it's from these destructive processes. And here's AEMIC seen in scattered light, one of the early images of AEMIC. So what we are thinking about when we're thinking about circumstellar disk evolution is what's happening to the planets as the disks evolve from protoplanetary to debris disk phases. And some of the big questions about debris disks that I'm going to be talking about for the rest of my talk are things like, all right, we're looking at dust, right? But how much mass is in unseen bodies like planets and planetesimals? Because that's really ultimately what we care about, is what's happening with the planets. So we're going to talk about that a little bit. What is the gas made of, and where does it come from? This gas is it's very recently discovered, so it's still pretty mysterious. And then how do planetary systems evolve in this critical age period from 10 million years to 1 million years? Or do they, right? Maybe they don't. They do, probably. So, all right, a couple of foundational concepts. One is that debris disks look different at different wavelengths. There are a couple of reasons for that. One is that different emission mechanisms operate at different wavelengths. So, for example, these are 3 images of the debris disk around Fomalhaut. at visible, far infrared, and millimeter wavelength. Oh, I should really swap out the JWST image. It's time to do that. It's time to put JWST here. So at visible light wavelengths, we've got scattering. At far infrared wavelengths, the thing that I wanted you to notice here is that this debris disk is eccentric and it exhibits what's called pericenter glow, which means that the part of the disk closer to the star appears the brightest. In the far infrared, there's a big R1/R² dependence because you have to irradiate the dust before it can blow back towards you. And also you have a temperature dependence, so the stuff that's closer to the star is hotter. But at millimeter wavelengths, we're getting something called exoplanet glow out here. And that's because this is all thermal emission and it basically traces and it's optically thin. So it's effectively tracing, I mean, it's optically thin at all wavelengths here, like I told you already, but it's basically tracing the density of dust as you go around. And the idea behind exoplanet glow is that because on elliptical orbits, right, y'all know about Kepler's laws, on elliptical orbits, particles spend most of their time far away from the star. And so that's where the velocities slow down. So there's almost like a traffic jam of dust particles far away from the star where the velocities get low. And that's what you're seeing here. There's a whole bunch of detail there involving eccentricity gradients and stuff that I won't go into. But basically, because we're seeing different emission mechanisms, this is telling us different things about the dust at different wavelengths. And then also, we have this rule of thumb, which I'll explain in a little while, that the size of the dust grain is roughly equal to the wavelength of observation. So not only is there different emission physics at these different wavelengths, we're also actually probing physically different grain size populations. And you can see that here in the AU mix system, where this is actually Kale's data in the blue contours here. So this is Alma observations of the dust disk around AU mix superimposed over HST observations of visible light. And it's not a sensitivity issue. We could have detected dust out past this wavelength. It's actually physically a difference between the millimeter-sized particles that are probed by Alma data, which tend to stay where they were produced in the gravitational potential of their planetesimal belt, compared to these tiny little particles probed at visible wavelengths, which are very efficiently blown out by radiation pressure and stellar winds. So the radiation pressure and stellar winds transport the small grains out, whereas the large grains really serve as test particles to trace the gravitational potential of the system. So if you want to learn about dynamics in debris disk, it's almost always best to look at the large grains. That's where Alma really has a role to play. So here's Alma. Y'all already know something about it, I think, but here's a little person for scale. These are 12-meter antennas, and there are a whole bunch of them that live up at 16,500 feet in the Altiplano in northern Chile, and you can move them from short baselines to long baselines. Long baselines give you high resolution, the short baselines give you low resolution. And it's amazing for studying debris disks for a couple of reasons. One is look at all of this collecting area. It's so sensitive. The problem with debris disks is that they are so incredibly faint. This will come up again, but compared to protoplanetary disks, debris disks are about 3 orders of magnitude fainter. It's really hard to detect them. So we need a lot of collecting area in order to be sensitive enough to see them. Also, not only are we interested in the dust, but of course we're also interested in the gas. And so these wavelengths are great because we have the millimeter-sized dust, which traces the dynamics. And then we have rotational transitions with small molecules like CO so that we can see what the gas is doing. And we also need the high resolution to figure out the dynamics there. So I've kind of organized my talk a little bit around the theme of the questions in the Alma Large program that I'm currently a co-PI on. So we now have a logo. This is our brand new shiny logo. So the ARCS program, this is the Alma survey to resolve exo-Kyper belt substructures. So even with all of the collecting area of Alma, it just takes a lot of time to observe these disks. And so we've been kind of doing, Alma's been doing sort of one at a time. But now we want to do a lot of them at a time so we can have a sample that allows us to compare structures across different systems. And so it has 3 goals. We're looking at 18 different debris disks at high angular resolution. We're going to resolve radial structures. This is one of the disks that has already been done at high resolution with Alma, one of the few small handful of disks, Keishi 107-146. So this is showing that there's a gap in this debris disk. We're looking at vertical structure, which I'll talk more about, and we're also looking at gas structure in the gas debris disk. So we have 18 targets, 8 of them are close to edge on so that we can do vertical structure measurements. And I think like half a dozen of them are gas rich, roughly. So I'm going to talk about each of these themes, and basically the rest of my talk is I'm going to go through each of the themes and tell you the story up to now, and then tell you what ARCS is adding to that story over the next year. So first, let's talk about radial structure, gaps and rings. How many of you have seen this picture before? Most, but not all. Okay. So protoplanetary disks, this is a D-sharp survey, which was a previous Alma large program led by Sean Andrews. I was also involved with it. That came out in 2018. So protoplanetary disks, we now know, thanks to Alma and D-sharp, are full of structure. They're just full of rings and gaps, spiral arms, all kinds of structure. And right now, we do not know whether or not the same is true of debris disks. We have started to get a hint that some debris disks have gaps. So my expectation, I will say, going into this is that, yeah, probably it's just all gaps and rings, kind of like the protoplanetary disks. Why wouldn't it be? It's probably like the same planet distributions, carving, the same structures. Maybe some of these structures are what turn into the planetesimal rings that grind down at later stages. So there are lots of reasons to believe that these are actually, that debris disks should inherit protoplanetary disk structures. And we had started to detect some gaps in debris disks. So I'll tell you a little bit about that story. So this is one of my students, Ava Niederlander. David knows her. Kale, did you overlap with Ava? No. Okay, so she was after your time. So this is a system called HD206893. And the cool thing about HD206893 is that it has a brown dwarf companion inside a debris disk. So this is a star that's been covered up. Here's a brown dwarf companion, and it fits right inside that debris disk. Okay, that's the scale of this system. And what Ava and I were trying to do is we were trying to use high resolution Alma observations to measure the location of the inner edge of the debris belt as a way of directly gravitationally constraining that companion's mass. Because as you guys probably know, for a lot of these young companions, you might say, oh, it's a planet, oh, it's a brown dwarf, but it's actually really hard to tell because you're comparing it to these models of hot start and cold start planet evolution. Really all you have is a flux point. You don't actually know how massive the thing is. And you have to know the age of the system, which we typically don't know for these young things. And so it would be really great to have a dynamical probe of the mass. So we were going to look, and there's chaotic zone theory that says, oh, it should clear out a region that's so big if it has such a mass, right? And you can probe that relationship. And so we expected that the inner edge of the debris disk would be here, but as you can see, it's really not, right? It has an inner belt, some inner fluffy stuff, and then it has a giant gap, and then it has some outer stuff. So we were trying to model this as like a single debris ring that got a little fluffy with maybe a star in the middle or something, but we kept having these residuals that were kind of in a ring around the star. We couldn't get low enough flux at these radii until we realized, oh wait, there actually is a gap at this location. So if you introduce a gap into the model, then your residuals go away. Hooray. So this was published in a pair of papers that came out. Faber Marino led one and Ava led another. And this was part of a trend where we were starting to detect gaps in these debris disks. So here's one by Meredith and Gregor. Here's another one by Faber Marino, a couple more by him. So we had like a handful of systems where we had detected these gaps. And so we were thinking, okay, probably all of the debris disks that we're seeing have gaps just like the protoplanetary disks. Now, if you make a histogram of everything that we knew before ARCS about belt widths. So this is the fractional width of these belts, delta R over R. So basically how wide is a disk belt compared to its radius. And so the protoplanetary rings, this is based on the ARC survey. Protoplanetary rings tend to be quite narrow. And then there are a few wider ones. There's sort of a long tail to the distribution of wider ones. But when you make the same plot for what we know currently about exo-Kyper belts, it looks different. So you can see it's a much broader distribution. We're missing a lot of these narrow rings. It's a broader distribution. And there's a giant lump out here with what seems to be a bunch of wide belts. And so the question that we're asking with ARC is, are these actually wide belts? Or is there unresolved substructure that we're not seeing, right? That's what we didn't have the answer to before ARCS, because we didn't have the high sensitivity, high resolution observations that we needed to distinguish between those two populations. And so this next slide is a little bit of a teaser. Yeah, Joaquin?
But there's selection biases here. So which
Yeah.
way, like, are they going, I guess in some cases they're going out of to see the wide space Kuiper belt?
Yeah, so these are high resolution, so these are high sensitivity, but not necessarily high resolution observations. So there's a whole potpourri of different resolution observations involved in this histogram. Whereas for the protoplanetary disks, we have these really nice uniform resolution surveys like D-sharp.
Okay.
Yeah.
So you think probably there's more biases on the debris side?
Definitely, yeah. Yes, so like I was starting to say, this next slide is a little bit of a teaser because I'm not allowed to show you the D-sharp results yet. So I've made them extremely transparent and stuck a giant logo over them. If you want to see them, you have to tune in to the Alma tenure meeting. So we've got this gallery of debris disks. This is like what, 12 of our eventual 18 sample. And as you can't see here, it turns out that so far we are not seeing a lot of substructure in these debris disks. So stay tuned for the official answer. This is really quite preliminary, but it actually seems like this result in this histogram might be holding up even in an era of high sensitivity, high resolution observations, that there just actually are not, there are a lot of wide belts in debris disks as opposed to protoplanetary disks, which tend to have much more narrow belts intrinsically. And that's really interesting. It's telling us something about planetary system evolution. What that message is, I don't know, but it is an unexpected result. I will say that. Yeah, Kale.
This is really trivial, but how can the width be greater than the radius? Like how can
Yeah.
it go up one?
Yeah, so basically if it's, so the width is kind of a full width half max, and then the radius. So if it were equal to 1, then the radius would be equal to the full width half max. So it would go halfway to its R. So it can be greater. It can be up to about 2 is the maximum it could be. Yeah. Okay. So stay tuned. Come join us at the Alma tenure meeting in December. You guys are all going to be there, right? Great. Okay. So with that teaser, I'm going to move on to vertical structure, and this is where Kale and David get their moment of glory. Characterizing the collisional cascade in the aemic debris disk. So first, a little bit of background. There are 2 basic assumptions that go into these measurements that I'm about to describe. One is that the collisional cascade is described by 2 power laws. The first power law is a number of grains as a function of their size. So basically, how many large grains do you have versus how many small grains do you have? So that power law index is Q. A is grain size, A to the minus Q. So that's, do you have a lot of large grains? Do you have relatively few large grains compared to small grains? The other power law index is P, and that says, how does the velocity dispersion of those grains depend on the grain size? Is it fairly uniform, where everything's in equilibrium and all of the grains of different sizes have the same velocity dispersion? Or is there some damping that affects grains of one size, but not grains of another size? And there's a lot of theoretical background to this, but this is a prediction based on Margaret Cannon Sculpting's model of what's called the collisional cascade, which is the way these grains grind down, that shows that where you are on this plot of P versus Q, those are the 2 power law indices, tells you something about, are you in what's called the strength regime versus the gravity regime? How does the velocity dispersion of the largest bodies compare to the velocity dispersion at a given size of the body? It basically tells you a lot about the physics of the collisional cascade and ultimately the tensile strengths of the bodies in the collisional cascade. So are these hard, compact spheres, or are they big, fluffy aggregates? So that's one. And the basic assumption number 2, which I've already mentioned, is that different wavelengths probe different grain sizes. So where does this rule of thumb come from? That the grain size is roughly equal to the wavelength of observation. Grains are like little antennas. So if you have a grain of a particular size, it'll be a perfectly efficient emitter at wavelengths that are small compared to its size. And then as you get wavelengths that are big compared to its size, it won't be an efficient emitter anymore because antennas don't do that. So if you have a bigger grain, it stays efficient out to longer wavelengths. And if you have a really big grain, it stays efficient out to even longer wavelengths. And so the turnover is roughly 2 pi a, the circumference of the dust grain, and it's because of that. So at a given wavelength, the large grains are going to be the most efficient emitters, right? Then you also have to think about the number of grains. So this is one of those power laws that we just talked about. The number of grains is a function of the grain size. The standard collisional cascade gives you a result that the number of grains as a function of their grain size is a power law with power law index A to the minus 2.5. That just means that there are a lot of little grains and not very many big grains. That's what that means. It's a steep size distribution. So what this means is that the small grains, because there are so many more of them than the large grains, even though they have a small surface area individually, they just overwhelm the large grains in number, so they dominate the total surface area of dust in the disk. So there are many more small grains than large, so the small grains dominate the surface area. And you put these two things together, and the net effect is that the smallest grain that can emit efficiently will dominate at a given wavelength. And therefore, so the smallest grain that can emit efficiently is going to be something comparable to the wavelength at which you are observing. So the grain size is then going to be roughly equal to the wavelength of observation. Okay, oh yeah, sorry, I lied. There was a third basic assumption. Basic assumption number 3, the vertical height encodes the velocity dispersion. So remember, we're talking about dust, and typically you don't have velocity information with dust, but if you're looking at an edge on disk, you can actually measure how vertically puffy it is, and that tells you something about the velocity dispersion of the particles. So if you have a star orbited by a Neptune, where every time a dust grain encounters that Neptune, it's getting kicked around really hard by the gravity of the Neptune-like planet, it's going to get vertically very puffy. Whereas if you only have a few little Plutos that are hanging around in there, it's going to stay pretty flat. And obviously this is an oversimplification, but it turns out that you can actually use this measurement, the scale height of the disk, and relate it to the total mass that's enclosed within the disk. So the wavelength that you observe at also matters, because this is a very, very old plot that I made. I think I made this like when I was a postdoc. But there's this paper by Philippe Thébault from 2009 that shows that you can only do this at millimeter wavelengths, because when you go to shorter wavelengths, actually the radiation pressure itself can vertically puff up the little grains. But remember, the big grains don't really feel the radiation pressure very much, for the same reason that they're not blown out into the halo and the AU disk. So once you get out to about 100 microns and beyond, it's really only the gravity that's puffing up the disk. So you have to do this at millimeter wavelengths, because at shorter wavelengths, there are other mechanisms that puff up the disk. Okay, and so this was from Alma cycle 3. We got these observations at AU. And this is basically just to show you that the scale height that you measure is a very sensitive probe of the total mass in the disk. And it's so sensitive that we can get down to just a couple of Earth masses of sensitivity by measuring the scale height of the debris disk around AU. So Kale did that. There's little Kale. Look at little Kale. Isn't he cute? Okay, so this is Kale's paper from 2019. And basically what Kale showed, he was the first one to measure the vertical height in the disk around AU. And he showed that the upper limit on the mass of the disk was 1.6 Earth masses. And the caveat here is that that only counts stuff where the disk is emitting, which is between radii of about 20 and 40 AU from the central star, which somewhat coincidentally, is the distance that Uranus and Neptune are from our sun, right? So we are actually probing the radius range of Uranus and Neptune in our solar system, and we're finding that the total mass between 20 and 40 AU is no more than 1.6 Earth masses. So there are no Uranus and Neptune analogs in this planetary system. Now, some of you may be thinking, wait, didn't I hear that AU has a planet? And the answer is yes, it does, but it's actually a lot closer to the star. It's too close to the star. It's not close enough to the dust to perturb the dust and make it puffy. So external perturbers or internal perturbers in this case are not ruled out. It's just we're making a limited statement, which is that from 20 to 40 AU in this disk, the total mass is no more than 1.6 Earth masses. So then think back to those power laws. That's where David comes in. Here's little David, there he is. Okay. All right. So the cool thing is that if you do this, so here's, this is now Kale's result, but it's in David's paper. So this is a 1.3 millimeters wavelength of Alma. People like to think of radio as a type of light, right? Except that when you look at a logarithmic plot of the electromagnetic spectrum, optical is like this, and radio is like this, right? It's a big stretch of the electromagnetic spectrum. So even with Alma, we can actually observe at quite a wide separation in wavelengths. So we went from Alma band 6, which is 1.3 millimeters, to Alma band 9 at 450 microns. And that's a factor of 3 in wavelength. So you can get a factor of 3 difference in wavelength, which means you can get a factor of 3 difference in grain size just with Alma axis axis. So here is the difference. So which of these looks puffier to you? You can be our MCMC algorithm here. Which of these looks puffier to you? This one or this one? And point up or down. Up, right? Yeah, this one's puffier. Yay! David ran a bunch of MCMC chains to prove that, and it's true. What this plot means is that band 6 is puffier than band 9. So this one is puffier vertically than this one. And so obviously we did a lot of like forward modeling and all kinds of details, but the basic answer is what you can see with your eyes, which is that this one is puffier than this one. And that is actually the complete opposite of what theory predicted. And we looked at it and we went, huh. And David spent a very long time writing and rewriting the discussion of this paper to be like, maybe it's this, maybe it's this. We don't really know. And I would say that's actually pretty much the state of our field. So another project that I'm really excited about coming up is this is the only system for which this measurement has been made so far. And we don't know, is AUMIC weird? We know that AUMIC is weird in a number of ways. It's an M star. It has flares. Kale knows all about the flares, right? It has very strong stellar winds. So maybe it's not a steady state collisional cascade. I don't know. But I just got time on Alma this cycle with A rank, so it might actually happen, to do all of the arcs edge-on disks, or at least I think a sample of 4 or 5 of them at band 10. So we're going to do this experiment with a bunch more systems to see, is AUMIC weird, or is there something we really don't understand about collisional cascade physics? Yeah, Tony.
So how close to exactly edge on what the system be?
That's a great question. And I think Kale and I did a lot of investigation into the degeneracy between inclination and scale height. And I think the answer is not super duper close. The cutoff that we used for the arc sample was 75 degrees. So we're doing vertical structure on anything greater than 75 degrees. Although formally in the MCMC posteriors, you can actually get limits or measurements, depending on how puffy the disc is, up to an inclination of, I don't know, 40-ish degrees. Like there are some systems that are very puffy that at 40 degrees, if you have a thin ring, it's pretty easy to tell actually. It's more when the ring gets wide that it gets harder to tell. Yeah.
But for these different elements, like what is the integration? How long do you have to like start?
Yeah, that's a good question. This one was, I don't know, several hours, like a few hours. And this one was several execution blocks. It was like 3 different execution blocks, I think. So 3 different, execution blocks with Alma. An execution block tends to be about 45 minutes. So hours of time. Yeah. But this is like one of the nearest, biggest, brightest debris disks. So this is like the low hanging fruit, right? If we want to do this for a sample, it gets a lot harder. So ARC's question 2 is so we did this for one system, right? We did it for AUMIC. There's one other system that we've done this for. This is the Beta Pictoris system. This is Luca Matra's paper from 2019. And the cool thing that Luca found is that actually for the Beta Pic system, you cannot describe the vertical structure with a single Gaussian like David and Kale did for AUMIC. That was fine for AUMIC, but for Beta Pic, you wind up with these wings. So you actually need a narrow component for the middle and a broad component for the wings. And believe it or not, that's exactly what our Kyper belt does too. And so our Kyper belt has a cold classical belt, and then it has a scattered belt, and that comes from the migration of Neptune through the Kyper belt. So the question that so there are only 2 systems where this measurement has been made at high resolution so far, AUMIC and Beta Pic. And now we're doing it for a sample of 8 more with our ARC's large program. And we're going to see how many of them have Neptune-like migration histories like Beta Pic, how many of them have Uranus and Neptune analogs, unlike AUMIC, right? We're going to answer these questions for a larger sample of objects. And this is the team of students and my postdoc, Brianna, who just started this fall, who are currently working on this. Anna just left to do her PhD at Harvard. And Jamar is applying for PhD programs this year. He's awesome. You should totally welcome him to your program next year. So this is my group of students that's working on the ARC's vertical structure right now. We're running many MCMC chains and we'll hopefully have results. Gas and debris disks. What is it like and where did it come from? All right, first, why should you care about gas and debris disks? Here's why you should care about gas and debris disks. Again, you should care about planets, right? Because we live on one. We like to know how many are habitable. We like to know where their atmospheres come from. So if you care about those things, you need to care about debris disks. This is a Nature Astronomy paper by Kantan Kral from the year 2020. And Kantan looked at this question of, okay, if you have gas and debris disks at these late stages at tens to hundreds of millions of years, what does that do to planet atmospheres? Does it do anything? And the answer is, yeah, it does a lot, it turns out, even when you have relatively little gas material. So this is looking at the gas to core ratio of exoplanets as a function of time in the presence of a gas-bearing debris disk. So this is the gas to core ratio of Earth, and then this is looking at different accretion rates from the debris disk onto the planet. And so for a plausible range of accretion rates, by the time you get to 100 million years, having this gas in the debris disk can completely overwrite an atmosphere like Earth, right? It's going to be more massive than the Earth's atmosphere just from the gas that's accreted from the debris disk. So it can completely overwrite a terrestrial planet atmosphere. And then for a giant planet here, this is looking at the mass accretion rate as a function of the atmospheric mass. You can strongly alter the C to O ratio depending on how much gas you accrete from the debris disk. So you can overwrite terrestrial planet atmospheres, and you can completely alter the C to O ratio of giant planet atmospheres, and that makes this gas really important. And the problem is that we don't know much about its composition or where it comes from. So the big dichotomy, this is how I like to present the dichotomy, is we don't know whether it's a protoplanetary disk that refused to grow up like Peter Pan and dissipate its primordial gas. So that would make it a very H2 rich composition, right? A very hydrogen rich composition, versus whether the gas is second generation produced through collisions like the dust in these debris disks, which would make it more cometary, like very low in H2 and high in CO2 and water and these other molecules. So that's important because we want to know what it's doing to the atmospheres of the planets that are forming and evolving at these late stages. And the answer is that despite our best efforts, we still don't really know which of these is the case. We have some guesses. This scenario is becoming more likely for a lot of the older systems, but there are still quite a few that could easily be described by this scenario. And I'll show you that evidence right now. So this is Grigory Smirnov-Pinchakov's paper where he looked at for models of different abundances. So this is basically like the Peter Pan scenario, and these are different versions of the second generation scenario compared to the measurements for CO and the upper limits for all the other molecules that we have so far measured. And you can see that our measurements and limits right now are not very constraining, are they? Bummer. We really can't tell the abundances. And so you might notice that the only thing with measurements here is CO. The other molecules all have upper limits. And so you might think, okay, well, what we really want to do is drill down on these other molecules. And we did that. This is my master's student Jessica Cliffmeyer's paper from 2021, where we stared at one of these gas-rich debris disks for 5 hours with Alma to try to measure the best possible limits on these molecules. And what Jessica valiantly pulled out of the data was a whole lot of nothing. So these are very deep upper limits for the 49 Ceti debris disk on a number of molecules that are prominent in both protoplanetary disks and comets, and there's just nothing else there. So the problem is that we don't know what these debris disks are made of. There are a couple of ways that we're trying to figure it out. And another A-rank Alma program that I have this cycle is doing some complicated craziness with optically thin line ratios and vertical structure measurements. If you believe that this is in hydrostatic equilibrium, you should be able to pull out the mean molecular weight of the gas just from the CO alone, which would tell us whether it's whether it's H2 dominated or not. But beyond that, the CO actually presents a number of opportunities that are pretty awesome, even if you don't know where it's coming from. So one of those that ARCS is exploiting is, you may have heard, in protoplanetary disks, there are planets that are now being detected through their kinematic signatures. This is an image of one of those from Christoph Pont's 2018 paper, where this is showing you what you would expect if the disk were in Keplerian rotation around the star. And this is showing you what they call a velocity kink, where you have some parts that are sub-Keplerian, some parts that are super on the planet, which in this case is located right about here. This is the HE16296 protoplanetary disk. So the cool thing about debris disks is they have a lot of CO, and the CO is very bright. So we should be able to do basically exactly this science with gas-bearing debris disks. And the only reason we haven't done it before is because nobody has observed debris disks at high enough resolution, because it takes a ton of time to do it. So we're doing that with ARCS. So ARCS question 3 is, how is the gas distributed, and are there kinematic signatures of planets in these disks? And with that, so that's the other thing that you can stay tuned for as the ARCS results roll out over the next year. So just to summarize what I've been talking about today. Debris disks look different at different wavelengths. The millimeter wavelengths are giving us those large grains that trace the dynamics of the planetary systems, which presents all kinds of opportunities. So we can now image gaps and rings in debris disks. And it turns out, surprise, they actually are less common than in protoplanetary disks. This is going to give us clues to how planetary systems evolve in that critical tens to hundreds of million year age range. The vertical structure is already telling us in just a couple of systems about the prevalence of Uranus and Neptune analogs, as well as Neptune-like migration histories. ARCS is going to extend that to a sample of 8 targets. And the origin of gas is still uncertain, at least for some systems, but we know that it's important in determining exoplanet atmospheric composition. So we're going to continue to drill down on the composition of these gas, of the gas at late stages. So I'm happy to take any questions that you have, and thank you so much for joining me.
Ryan, I know you had one on Zoom that you were mentioning earlier.
Oh, sure. So let's see. So I guess one thing is all the dust that you're seeing ultimately comes from collisions, right? This is a destructive mechanism. What do we know about the collisions?
What do we know about the collisions? Right. Well, what do you want to know about the collisions?
So what's assumed, and what do we know based on the solar system? Is there any chance in the solar system seeing examples of the collisions happening? Like what?
Yeah. So I didn't include this image in my talk, but right around the end of my PhD, so it would have been around 2010 or so, the Hubble Space Telescope captured this gorgeous image of a collision between 2 comet-like asteroids in the asteroid belt, where you can see these 2 rocks colliding, and they're producing a gorgeous trail of debris dust. And it was totally beautiful. And I remember looking at that with my PhD thesis advisor, David Wilner, and we were like, that's it. That's the dust that we're seeing in these debris disks. So, so we have seen an example of this with HST. I think basically just one example. Although, I mean, I think there are a few other times in the asteroid belt we've seen like a little trail of dust, and we're like, that's probably a recent collision, but we haven't seen it as in the moment as in that system. And I think the other answer to that is truly that not enough is known about the collisions in these planetary systems. I think this comparison of the vertical structure at 2 Alma wavelengths is one of the most promising ways of getting there, because that's actually going to tell us about the level of damping and the collisional, the tensile strength of these bodies in the collisional cascade, and hopefully whether they're kind of fluffy aggregates or more porous. We have some hints about that too from spectroscopy, although it's really hard to tease that out from the spectroscopic results.
Cool, thanks.
Yes.
Well, one thing I've always wondered, and now that I know more about astronomy, well, this debate is but so clearly Alma can detect and resolve debris disks, right? But what will it take technologically to actually detect the actual Kyper belt analog? Is that NGVLA? Is that like, have people kind of done the math and figured out, like, is that 10, 15 years away, or is it like just not possible?
That's a great question. So it depends to some extent on how much observing time you're willing to devote to a project like that. But I think the answer is that with kind of the next generation Alma, not the wideband sensitivity update, which will help, but like the Alma ×10, which they're hoping to do in the 2030s, we'll see if this ever emerges. That would do it if you were willing to devote a fair amount of observing time to this project. And I think some of the sort of farther future infrared telescopes could get us pretty close, but you basically just need a lot of collecting area. You need a lot of collecting area and a lot of bandwidth to do it properly. So something with a lot of collecting area, something with a lot of bandwidth. Alma ×10 could do it, but not a lot on the horizon immediately.
And my follow-up, this is a far more serious question, but you know,
I'm sure it is.
Professor Hughes, you have taught so many students over the years. Just off
Who's
the
your
top,
favorite, right?
Yeah. There's one in particular that, you know, maybe one you advise, or damn it, like, you know, just one that, you know, who might be like the shining star.
Let me consult my Ouija board over here. I love always. It's, I sometimes joke that one of the things that has taught me the most about supervising a research group is reading the book Siblings Without Rivalry after I became a parent to try to prevent rivalry among my own children. And I think I'll take a page out of that book and say that I appreciate each student for the unique.
So, we know that David knows more about astronomy, but one worries about his MCMCs. And so, for prior distributions for figuring out vertical structures, what do you actually have to assume about this? Does the star not actually impact vertical structure?
Yeah, so at these wavelengths, basically the answer is no, we don't care about the star. Although the problem with AUMIC is there's a honking bright star in our image. At radio wavelengths, we're used to not having to deal with stars. I actually remember when I was a grad student, I used the SMA to observe Vega to look at its debris disk. And I was reducing the data and I saw this image. I was like, what is that point source in the middle of my field? This debris disk should not be a point source. It should be a big ring. And I was like, oh, it's a star. Look, it's a star. I saw a star. So Vega was the first star that I saw with a radio telescope. AUMIC is probably the second or third star that I saw. So both Kale and David spent quite a bit of time, especially Kale, spent quite a bit of time and effort trying to figure out what to do about the star. Basically, what we did is we wound up modeling it as a point source. Unfortunately, it's variable, it flares. Kale had to remove the flare from the band 6 data, which we wound up having to throw away the data. You can't, this flare, it was changing too rapidly. You can't fit that. Although Kale gave it a valiant effort. But yeah, and so it also varies. And so like for David's example, where we had 3 different dates of observation, we had to just fit it with 3 different fluxes in our models. Luckily, it's a point source, so that's pretty easy to fit.
Sure, but since you brought up the fact that it's flaring, when we see stars like the 38 Mon,
Yeah.
they do show extreme asymmetry about from all of the previous images. So why is it that the debris disks aren't detected, whereas all the gas that's these things?
Well, so actually that's another point. I mean, the debris disk is affected, but it's only the small grains that are affected. So like actually, if you look at AUMIC at infrared wavelengths, there's all kinds of stuff going on in that disk that is probably due to the starlight at some level. So there are these fast moving features in AUMIC that you see at infrared wavelengths, and we don't see them at millimeter wavelengths just because the grains are too large to be affected much by stellar radiation pressure.
But I mean, you need to have this argument in graphical how you would do operations.
Yeah, right.
Other than Meredith.
So for your top example, what would cause a ring like this to be eccentric and maintain that eccentricity over many orbits? So that's the
Maybe. So people have been looking for the planet that is sculpting the Fomalhaut debris ring for quite a long time. Some of you may or may not be aware of Fomalhaut B, which was a planet candidate detected with HST as a point source, and it has this wacky history where they observed it over time. They when they found it, it was this point source right inside the ring, and as Paul observed it over time, he actually showed that it was on a ring crossing orbit, like this thing is going out of the ring, and it was also changing in flux with time. So it seems like it was probably a dust cloud from a collision that is spreading out over time. So it was a real thing. It just probably isn't a planet. But it was probably marking the collision between 2 planets. I think we were all hoping that the JWST images of Fomalhaut would show us the planet that's sculpting the ring. The first one that came out didn't, but I believe that was that NearCam or MIRI? And whatever it was, the other one is the one where the planet contrast should be higher. So we're all waiting for the other one to come out now to see if we'll see a planet there. But yeah, it's got, I mean, I don't know. So there are some theorists who try to explain these eccentric debris rings in other ways. For example, if you have small residual amounts of gas at late stages, which we know Fomalhaut does actually, it has a CO detection. Maybe if you have an eccentric gas ring, you can apsidally align the grains and make them into an eccentric ring as well. But honestly, I think those models are a little contrived. And they depend really strongly on the initial conditions that you put into them. So I think it's probably planets, we just haven't found them yet. Yeah.
Kale asked you about Kuiper belt objects with Nectar and Alma, but has anybody taken the Earth, the solar system itself, figured out how it might look in Alma and in the debris disk world, and try to find analogs for anything that might look like our solar system rather than looking for just exoplanets?
Yeah, so I would say, so the problem with dust in our Kuiper belt is that it's actually really hard for us to see it from where we're sitting. So we actually know less about the distribution of dust in our Kuiper belt than we do about the distribution of dust in these other systems. So people have tried to model what would Uranus and Neptune and Pluto's current orbits do to the dust in the debris disk. But these models actually undergo a lot of the same limitations that our models of other debris disk bearing systems undergo. So for a while, everybody thought that when we looked at debris disks, we would be able to tell if there was a planet there because we should see lumps of dust at basically L4 and L5 trapped in resonances. And when we started looking at debris disks, we did not see those lumps. And so then the theorists went back to their chalkboards and they crossed out some stuff and they added some other stuff. And then they came back and said, aha, we know why that is. The collision rate is too high. So if the collision rates get high, that can actually smooth out the structure and you don't get those resonant clumpy structures. So that's probably what we're seeing here. The collision rates are too high for us to see those clumpy structures. So we've tried to use the solar system as a model, but it hasn't really helped because we don't understand debris disk physics well enough to know what our own solar system's Kuiper belt is doing in terms of its dust. We get some data from spacecraft that pass through the Kuiper belt. So there's a dust counter on New Horizons right now that's returning a lot of interesting data, but that's like one line of sight through the debris disk.
Any last questions? If not, let's thank our speaker. Thanks doubly so because Meredith is actually going to be leaving tonight to get the Amtrak back to Chicago and then fly straight away. So we're going to be taking her out to dinner somewhat earlier than our speakers. If you'd like to join us for dinner, meet us basically like right now outside of the lobby.